Okay, so let's start off where we started last time. So last time we were talking about like how to design Altium stuff, basically Altium stuff like schematics wise, right? So how to get components and how to basically put them into your schematic design. And as you can see here, I kind of added on to like what I did last time. I kind of just finished the circuit uh, from the um, from the FSA intro project. So as you can see here, I have my my photo resistor basically, my potentiometer, and then I have another potentiometer right here between this part and this part, the positive terminal of the comparator and the output. So this is just hysteresis. And then I have my essentially the control of this comparator basically controls this BJT transistor to essentially power to provide the amount of current needed to power this coil for this relay right here. So I basically have this is basically everything in the main. So this is the main circuit right here, right? And I have these two outputs of this circuit, right? Using ports. Hold on, give me one sec. Just move this right here. So yeah, so I have these two ports basically as output, and I basically need these guys to connect to my connector schematic right here. So so I have a separate schematic for connectors, which is like a pretty good idea when you're designing stuff. When you're working on a project in Altium, I'm going to expect you guys to essentially do something like this, where you basically have like your main circuit is going to be in one schematic, and you're going to essentially make a new schematic by right-clicking on your project and adding new to project. So yeah, this is my connector schematic. Usually, it's a lot more full because you can have like a lot more connectors in this schematic, but for this simplified design, I only have one connector here. So I'm going to go ahead and copy this port, and I'm going to essentially connect that over here to this J1 connector. And what I'm going to do now is I'm going to see like, okay, so this connector schematic, right? It's kind of uh, like I feel like this schematic is like sheet is kind of too large for this one schematic symbol here. So what I didn't get to show you guys last time was essentially you can if you click if you're not like on if you haven't stuck in anything, right? So right now I haven't stuck in anything. What I can do is I can on the by clicking panels on the bottom right and going to properties like this, I can essentially can basically control properties of the overall schematic. So like for the selection filter, I can filter like what components I want to like select. So if I only want to select, let's say, like components, then it will basically not select anything else except components like that. See? So that's sort of what the selection filter does. It lets you select different kinds of like components or properties of um, in Altium. So that's the first part. And the second part that I wanted to show you guys was the general like schematic sheet layout. So you can see here, you can control the snap grid. So how much it snaps like this, you see the grid of the actual schematic. I don't usually change this too often, but like if you needed to change it for something, you can change it here. And you can also control the most important probably thing that you can do here is the size of the sheet. So this is like I'm honestly doing this like pretty often when I'm making schematics. Is I determine the size of my schema like of the circuit, and then I basically uh, size the schematic to fit that circuit. So when you scroll all the way to the very bottom, you can see here you can basically determine the sheet size. So um, this sheet size right here, you can either have it in portrait, which why would you do that? Or like normal people, you have it as landscape. So it's going to be in landscape, and the only thing you really need to change here is the sheet size. You click on this arrow, right? and this arrow will basically show you a bunch of different sheet sizes you can do. And the way it works is the lettering, A0 is the smallest, and then as the letter increases, it gets larger and larger. So A0 is the smallest you can do. So, oh wait, no, sorry. A0 is the largest you can do. My bad. Um, as you can see, um, A is the smallest you can do from the standard sizing. And then as you ink go, B goes larger, C gets larger, and then E is like really large, and then A0 I believe is the largest. So that's from standard sizing. Let's say I wanted to go even smaller for some reason, like what you can do is you can go to custom, and you can essentially choose the width and height of your schematic. So in landscape, you would basically control the width by putting in the exact sizing you want. So let's say you only wanted to do, okay, let's do 8,000. 8,000 mil by, let's say, 5,000. Oh shit, I bet 5,000 that. That's really small actually, so let's do a little bit larger. Let's just say, let's just have it like this, right? That's fine. Like your circuit fits into this little schematic here, right? And I think that's all that matters. It just makes it easier to see your stuff. Just sizing it to the schematic is just the sizing your schematic to the circuit can kind of help visualization and stuff like that when you're looking at it. So that's kind of the only like really reason you have to like size smaller. But if you have a really large schematic, like if let's say something big, like if you need more space on the schematic, what you're really going to be doing is you're going to be going into properties in the properties panel, and you're going to basically increase the size of your schematic by just going to a larger like letter like that, for example, right? You have more space now. So without further ado, though, let's talk about the main focus of today is actually going to be PCB design. So before I like start anything, I just want to say like um, I myself am not like in any way, shape, or form like really like knowledgeable on this topic. Honestly, PCB design is a very like complicated like it's something you basically are going to be doing for like a large portion of your life. Like if you go into EE, like it's you can always improve your designs. Um, like there's a lot of different techniques you can do, and honestly, uh, very small little things you can do to essentially like make things better from an efficiency perspective. There's a lot of different aspects to PCB design, so I'm not gonna because I don't want to like over saturate this like knowledge transfer with like information that's not necessarily necessary. I'm going to try to limit my talk up just about PCB design from a very general standpoint. So designing PCBs that will work, right? So without going too deep into like all of the specifics for improving, like for example, like signal integrity, like things like that. I don't want to get too deep into that, like just because it's not something you really need to like uh, worry about right now. Like I'm sure you will get to a point where you will need to worry about that in like your future career. But that's something that you can kind of learn more on your own as you get like more advanced. Like once you get the basics out of the way, you'll kind of pick up more and more like wisdom in terms of like um, how to design your PCBs. So uh, let me just start by actually before you can ever actually make a PCB, the very first step is you have your schematic, right? You want to before you can even make your PCB, you have to actually um, validate your project. So I'm going to first do that really quick. So on the top like left corner here on project, I'm going to click validate PCB project. And it's going to let me know if there's an error. If you click on this button and nothing shows up, that means that your project has no errors in it. So that means that you're good to go to the next step in the process, which is making a PCB. So let me just go ahead and do just that. So on my projects, on this project's label right here, right? I'm going to right click on it and I'm going to click add new to project, but instead of making a new schematic, I'm going to make a new PCB actually. So it's going to be the second option. And once you do that, you're gonna see this. So you're gonna see like a default outline of your PCB. Right now, it's just a square with default sizing, right? Before you do basically anything, before you even import all of your actual like components to your sorry, to your actual PCB, you actually need to kind of modify a few things. Um, the very first thing I always do when I make a new PCB project is I'm going to actually align this origin. I'm going to set this origin right here. I'm going to set it to the very edge, the very left bottom corner of the PCB. That's sort of really useful for when you're doing any kind of measurements on your PCB. Having this origin point is basically like your reference point. So like it's going to basically be necessary for when you're measuring stuff and things like that. So um, let me just say this as well. Sorry. So yeah, so basically the first step is you're gonna click edit and you're gonna go down to origin and you're gonna click set. So setting your origin to this point right here is very useful. So that's the first step, right? Once you have that, you're gonna your next step is gonna be determining I mean, there's like I would put this all under just like pre design checklist. So there's no like particular order in which you have to do these things, but I'm just gonna show to you how I would usually go about doing this. So the first thing I'm usually gonna do is I'm gonna decide if my PCB is going to be a two-layer PCB, a four-layer PCB, a six-layer PCB, etc. So the way you do that is you're gonna go to design and you're going to go down to layer stack manager. So when you click layer stack manager, you will actually see the stack of your PCB. So to give you guys a little understanding of like how PCBs are made, they basically stack different materials. So you have your layer that's going to basically be your like your solder mask layer, which is some one kind of material, right? It's like a dielectric basically. And then you're gonna, or yeah, it's basically covering your signal copper layer, right? So your main layers are going to be basically routing like things called traces, which are basically just like copper connections on your PCB. They're going to be on these layers, right? These copper layers. They're like going to be like either called signal or they're going to be called plane. So this signal layer, right, is going to basically be like one huge sheet of copper, and then the PCB manufacturer will basically cut out the copper um, with like a special like a machine, like a certain machine that basically cuts out the copper to basically outline your PCB, kind of like this. So all of these like red and blue lines stuff are basically just pieces of copper that are basically cutting the copper layer out to basically fit these connections. So that's going to be what these are, right? These layers right here. And then another important aspect is the dielectric layer. So in between each copper layer, there's a thin layer of dielectric between. And this is usually FR4 if it's like if it's the core. So the core of your PCB is going to be FR4. But I want to, let's say I want to do a four-layer board for whatever reason. The way you're going to do that is I'm going to click add. I'm going to select this top layer right here and I'm going to click add, and I'm going to add a signal. Actually, hold on. Let me do it like this. Or yeah, let's do this one. I'm going to add a signal layer below. So when you do that, and this is going to automatically include, it's going to automatically include dielectrics between your layers. But let's say I want to have two middle copper layers between these two. I'm just going to click add on the top and I'm going to click below. So I want to add it below this layer. And I'm going to click signal here and I'm going to click OK. And you're going to see now I have two extra copper layers essentially in the middle of my like the top and bottom layers of copper. There's two new middle layers of copper basically that you can basically route to. And it's going to be between it's going to be a different like prepreg. It's basically like a composite material. Dielectric is in between, it's like thinner. It's going to be much thinner than your like dielectric core. And without going too in depth, it's basically just sort of like an extra dielectric thick material in between, sort of like this core actually adds a lot of importance to like the rigidness of your PCB. So having this core in the middle sort of adds like a rigidness, like so it doesn't like break as easily. So this thick core is essentially doing that. It's sort of like your main uh like um rigidness of your PCB itself. So it kind of keeps everything protected in that sense. So that's what that's for. Aside from obviously keeping like insulation between the layers, right? That no actual current is flowing between these layers. But I will go into depth how you can actually route um, layers between these layers in a bit. So once you have your stack up ready, um, you can go ahead and move on. But before I do that, I just want to really quickly elaborate a really important aspect of PCB design, especially if you're going into like power electronics, is the weight of your copper planes, basically. So your copper planes, the weight of it is sort of determining the thickness. So the weight and thickness are directly correlated. So if you increase it, um, you will immediately see that your thickness will increase as well. So that's sort of it basically the weight just determines like the amount of copper you're basically putting onto this layer. So why this is useful, right? So if you need a if you're so your trace is basically a trace is just a copper connection on your PCB, right? Your PCB needs to be able to actually properly carry the amount of current that you necessarily need. Especially the max current is very important. So not just like generally current, nominal current, but like max currents as well need to be considered for your load. Like if you have a load, right, you need to understand how much current will be flowing through a trace, and you need to properly essentially uh, size your trace, your copper trace, to meet that expected current carrying load, right? So that's one aspect of that is your copper weight. So increasing copper weight will increase how much current you can carry in a trace, like automatically. Like no matter the dimensions of your trace, increasing the copper thickness of your trace will automatically increase how much current you can carry. And the calculations are a little bit tedious, so I actually use separate software to do those calculations. But for all intents and purposes, you don't have to worry too much about that right now. For right now, we're going to go with 1 ounce copper. So 1 ounce copper is generally the standard for PCBs. It can carry like a generally decent amount of current. Um, and it's not necessarily used for like power electronics. Power electronics generally uses 2 ounce copper, but for our intended purposes, 1 ounce is just fine. So now I'm done talking about that. I'm sorry about that. So let's actually move on to the next step. So the next step is going to be essentially your rules. So really important aspect of PCB design is making sure that you follow all the rules that you need um, in order for your PCB to get manufactured. So um, there's I will split rules for simplicity. I will split rules into sort of two categories. The first category is going to be rules that are required by your PCB manufacturer. So your PCB manufacturer can only allow certain specifications of your PCB, like just literally manufacturing capabilities just limits like how close you can have certain traces, for example. Like trace clearance is one of those like rules that you need to follow for manufacturing. So you have manufacturing um, like rules, but the other aspect is also actually your rules related to um, essentially like it's kind of like related to more theoretical aspect of design. So, like for example, right, if you have like a trace with like high voltage, right, you need to have certain rules, certain clearance, right, distancing between a high voltage trace and a lower voltage trace, right? And that's just kind of like helps with a lot of aspects actually in PCB design. In one aspect, it sort of helps with um, like return like feedback. So return loops basically like going back to ground. So there's less noise essentially when you have like higher voltage traces separated from lower voltage ones. Another aspect is also isolation. So having isolated traces between high voltage and low voltage just helps overall EMI. Like it prevents certain issues with your board, like an EMI perspective. So um, it's also just overall protection of the board. So having high voltage traces away from lower voltage ones also protects from like current surges and voltage spikes and things like that. So it basically is very useful for those kind of aspects when you're trying to isolate uh, voltages on your board. So basically, those are the two kinds of rules you're going to have to consider when you're designing a PCB. So let's go ahead and actually um, specify those rules in the rules constraints editor. So this rules constraints editor is basically your way of understanding like what rules you basically have to follow and what Altium will bug you for later when you're trying to validate your PCB. So um, the most important one is going to be clearance. So at the very top, you'll see there's clearance constraints. So it's kind of like a pyramid of values, but for track, right? The lowest in this case scenario, the closest you can have two tracks, like two. So a track is just a trace. They just call it track in Altium for some reason. So trace to trace clearance has to be at least 10 mils. That's basically what it's saying. So it needs to be 10 millimeters apart. If they're closer than that, then you'll get an error, like a green marker on your PCB. So without kind of going into like every single like uh distancing that you need to have, I'm going to instead tell you a really cool way you can actually import rules into your project based on your JLC based on okay sorry not JLC but like based on your PCB manufacturer capabilities. So for us, right, we use JLC. So um automatically we're going to have to import a rule, like a rule file uh, from JLC's essentially uh, capabilities. So JLC actually provides a .rule file which I can send to you guys if you guys can't find it. But usually you can find it if you just search up JLC.rule, like or actually for Altium. Generally speaking, you will be able to actually I found it on this GitHub page. That's how I found it. The design rules are just saved here. If you go here, you'll see like the layer for the rules for all JLC for a 4-layer will be 4-layer 1 ounce rule will be this one right here. So I've already saved all of these rules on my computer, but if you need to like I can definitely send it to you guys if you need it. But it's a nice way to not have to like go into all the rules yourself to determine like all the sorry like all the basically what JLC's capabilities are. You can it basically just gives you all of those um rules right here. So to actually do it though, you're gonna have to basically click on design rules and you're gonna have to go into import rules. So you're gonna right click on here um and you're going to scroll down to import rules. And from here, this is the tricky part. You're going to have to click Control A to select all rules, right? Because you're basically importing rules for everything related to JLC PCB capabilities, and you're going to click OK. And then from there, you're going to basically it's going to ask you to open a rules file. So the extension is .rule, and I believe I have it saved somewhere. Let's see. Yeah, right here. So we're doing a 4-layer 1 ounce rule. I'm just going to put that in and it's going to replace everything with the rules that JLC has. So you can see it already changed all the values for me by just importing it like that. So it's a really good way to get an idea of like what the actual rules will be for JLC without having to actually put everything in yourself, because that would be like a really painful experience. So I'm going to click apply and I'm going to click OK. So now we have all the rules we need. So we're basically just about ready to start working on um, like the actual design now. So basically, right, let's say you want to make your PCB a certain shape, right? um, the first thing you're going to do is you're going to go to mechanical one and you're going to outline your board. Or actually, before you even do that, the first thing you're going to do is you're going to go to, you're going to click one on your keyboard, or you can go um, into view and then click board planning mode. It will basically, this is where you basically decide the dimensions of your board. So let's say you want your board to be a certain size. So let's make it like 1,800, 1,800 mil, like around there. And let's make it like by like 1,000, like that. So I decided to make my board about this big. So let's go ahead. And so once we've basically, I've decided like the dimensions of my board, I'm going to go back to I'm going to go back to 2D layout mode, or I'm going to press 2. So by doing so, you're now back in your layout mode. And in here, I'm going to basically outline the dimensions of the board on the mechanical layer. So the mechanical layer is used by your PCB manufacturer to kind of like um, to determine like the outline of your board. But it also lets you kind of like make like different shapes like to your board. So let's say you wanted to have like a round corner or like an edge to your board, you can basically do so by using this mechanical layer. And yeah, I would recommend just using this if you need to change the outline size of your board. So let's say you want to have like a board that's like shaped like this, right? Like some weird kind of dimensioning. Like you would basically be able to do so. Let's say you want your board to look like this. Uh, right? So you basically outline like a more complex shape than than what's like actually than what you actually need. So than what you actually basically had from your dimension. So you've set your dimension, right? But now you're basically cutting out parts of your board um, this way. So let me give me a sec. Actually, let me cut that out. So I'm gonna just show you really quick how I can not only make like a weird shape, but I can also actually put rounded edges to my board. So basically to do that, um, I'm just going to right click on this place line part right here on this end here, and I'm going to go to arc edge. So on arc edge, on this option, I can basically put like different edges to my board like that. That that way. Okay, cool. So now all I have to do is I have to select this whole thing, and I'm just going to go to design, and I'm going to go board shape. So from design down to board shape, I'm going to define board shape from selected object. It's going to just cut everything out from this. So this is my mechanical outline of my board. So once I have that, I'm just going to click project. I'm going to click um, sorry, give me 1 second. I'm going to click import changes from FSAE, like from your schematics, and it's going to basically um, show you all the components you want to add to your board. So I'm going to click validate. Everything should be green. That's okay. I'm just going to ignore that for now. But yeah, so basically all this gets added. I'm going to click execute, and it's going to basically add all my stuff to my PCB now. So okay, I actually made this way too small. Fuck. But yeah, I'm not going to make the whole PCB, but I'm going to really just quickly show you um, just some ideas as to like um, how you can basically route um, certain connectors and things like that. So let's just say I want my connector to go like here. And let's just really quickly, as you can see, by the way, too, you can actually, Altium will let you know if you're like breaking a rule, by the way, with this green error symbol. That's what it means. It's basically saying that you're breaking some kind of rule that you've already set in Altium. But if you wanted to work around the rule, all you have to do is click reset error markers and just go away. But yeah, that's sort of how you do that. And then I'm just going to put that right here. Or actually, the mounting hole is really important. The mounting hole is here. It needs to be on the PCB itself. So make sure it's like that. So that it's rules compliant. And then this is now mounted to your PCB. Let's just route this comparator really quick. So the first thing you'll notice is basically you have these wires, these like lines that go to different nets, basically, that have to basically be connected. So this means that you have to essentially connect all of these with like a trace, so copper basically, right? So I'm gonna wire this actually kind of like this. So I'm gonna essentially let me first provide power to my comparator, right? So this guy right here has two pins here that need to provide power, and it's going to basically be coming from the connectors, right? 1 and 2. So let me just do that really quick. Let me just route a trace. So the way to do that is you're going to click either Control W like this, or you can also just click interactively route on this top, like this really middle right here. It's going to automatically show you. It's going to show you like this like crosshair, and you, from there you can basically route copper to your PCB. But from the get-go, I just noticed like this trace is like really thin. So if you, let's say you needed like a lot of, let's say this comparator needed like more current running through it, right? Without doing any calculations, just like from bare bones, you can kind of overestimate the sizing of your trace by just going over, right? So like without doing the exact amount of current the copper trace can actually carry, you can just overestimate. And to do that is you can either double click on your trace and click, let's do 10 mil, right? So let's make it like beefier. So let's just do 12. This is gonna be able to carry like a considerable amount of current. Like if you're doing 12 mil, even a 15 mil, like you can just kind of like there isn't like an exact limit to how big your trace can be, but that's, you can either do that and you can continue routing. And let's say it's going to continue the same size, but let's say you wanted to change the width of your copper as you're going along. You can also click on tab and you can actually pause your routing to continue to make changes. So let's say I want to do like 10 mil now. It will actually, or you actually have to first click down and then you can click pause and you can go 10 mil like this. See, now it's a bit smaller. So stuff like that. So that's how you would route copper to your connector like this. But let's say you didn't want to use a trace to connect your power, which is very common, by the way. You're typically going to instead want to use something called a polygon plane. So a polygon plane is essentially just cutting, instead of using just like a singular wire trace like that, you can essentially make a really large, essentially cutout of copper, like a large piece of copper you can basically use as like a plane. And it can basically go through like a bunch of stuff. So you can make this entire layer actually 12 volts this way, like this. Um, there's a way you can actually also make it around this, but um, I'll leave that for another. Like if you guys need, like you don't necessarily have to do that. So I'm just gonna let it kind of go around like this, and just kind of go like polygon like this. Should be fine. It's like that is fine. So yeah, here's your polygon plane. So you now have basically all this whole region, right, is all copper, and you can basically make it to a certain net. So let's do P12, right? So P12, once you click P12, you're gonna have to re-pour it, and it's basically gonna connect everything that's connected to P12 is gonna essentially connect to this layer, right? So you can see P12 is connected now on this comparator, and P12 is now connected to this connector. And if you needed any other P12 connection on anything else, like for example, this diode right here, you're gonna have to report it, but once you report it, you'll see that it will now connect to P12 like that. So that's how these polygon planes are basically used. You can basically connect a bunch of power connectors like here, P12. You see how on my schematic I have a bunch of P12 connections everywhere? It's basically gonna connect everything to this layer of copper like this. Um, okay, last thing I'm gonna talk about today is I'm gonna talk about vias. So really important, right? Let's say you wanted to route some trace something, right, to another layer, right? And you wanted to come back to the top layer, right? So basically routing to different layers. The way you do that is you're gonna first click um, on place via on this top here, and you're basically gonna place that somewhere. And this via is basically gonna route to a bunch of different layers. It's basically gonna route all the layers together, right? It's gonna connect all the layers into this one copper basically hole. So this via can essentially connect different layers to each other in that way. So uh what it's gonna be the way you can basically do it is you can either have it like a blind via, um, which I'm not going to talk about today, but let's just do like a regular via. So regular via goes through all the holes. It goes, you can actually see through it. It's like a through hole via, right? Um, the first thing you're going to do is you're going to place your via, and you're going to basically, what you're going to do is you're going to essentially, um, like, uh, connect this via to a certain net, right? Let's do the net that it's going to connect to. Let's just do comp out, right? So it's going to want to now connect to this net right here on this comparator. And this will essentially be done by going to another layer. Let's actually, because um, this pad on this comparator, right, is on the top layer. So what you're going to have to do is you're going to essentially have to route trace. Let me get this out of the way. I'm going to move this like that. And I'm going to go to another layer. And I'm going to route on this other layer on the bottom here. You can see all the different layers. I'm going to route on layer one, this middle one right here. I'm going to route it over. Actually, where's comp out? I think it's connected to this. Um, where is it? Where is it? To this one right here. Okay, cool. So this guy right here. So you can basically use um, this via to connect to this connection on this layer by just clicking on route, and you from this via onwards you can connect to it like on this other layer, and you can see it's a different color, right? So this color represents like a different layer that you're routing on. So let me just really quickly repour so you can see better. Actually, hold on. I need to get this guy like that.